We proved linearity of expectation, which is that the expectation of x plus y is expectation of x plus expectation of y, and this was without any assumption. So, you will see in this course again and again the great usefulness of this simple property. So, let us start with this example of putting letters into n envelopes which are addressed in a random way. Okay. So, the question is, or the random variable we are interested in is what is the number of letters which were correctly posted. So, what is expectation of this x? Okay. So, if you do it by definition of expectation, so simply by definition expectation is probability that x takes value k times the value k, right, for all k 0 to n. So, 0 also because maybe no letter was posted correctly, and that probability, recall, we have actually evaluated and it came out to be a complicated expression, right. It was something like in the limit it was 1 over e, but otherwise in general it was quite complicated. So, computing these probabilities is not easy, and hence this expectation also looks a lengthy calculation. That even probability of x equal to 0 was complicated. Right, this it was an example of inclusion exclusion principle for probability. So, is there a way to get a better sense of this expectation? So, let us do that. So, define xi to be focused on only the ith letter. So, if it is 1 if ith letter is correct, if letter I is correctly placed. Okay, and 0 otherwise. So, now if you go over all the letters, then the sum of these xi's is your variable of interest. Right, which means that expectation of x is expectation of sum, which by linearity of expectation is sum of expectation of xi. So, what is that? So, this implies that expectation of x is, so expectation of xi is essentially the following expression. So, it will be 1 if the letter I is correctly posted, and what is the probability of that? It is unique, right. So, it is just one case 1 over n, and 0 otherwise, which is n minus 1 over n. So, that gives you 1. Okay, that is the answer. So, almost immediately by linearity of expectation you get that you expect only one letter to be correctly posted. All the n minus 1 will be wrongly delivered. Okay, that is the expectation. In expectation, it may not happen, but that is what you are getting by probability calculation. So, this became a really easy calculation, and this is what you will see many times. If you correctly partition, if you correctly use linearity of expectation, then complicated expressions will greatly simplify your life. Okay, so with that example, I hope linearity is clear. Let us now move to random variables which are famous, which appear in many areas. So let us start with the discrete first. Okay, so first example is probably the oldest named example is Bernoulli random variable. This is toss a coin where the probability of getting a head is not half but p. So it's a possibly biased coin, and define the random variable to be 1 if head appears, 0 otherwise. Okay, so the mass function is either x takes 0 or 1 value. So it takes 1 value with probability same as probability of head, which is p. Okay, and the other is x equal to 0 probability is 1 minus p, and you have these properties that expectation of x is probability of x equal to 1 times 1 plus probability of x equal to 0 times 0, which is equal to just p. P is the expectation, right. In particular, you can notice that it's not 0 1. Right. So this is a simple example where the expectation may not actually be a feasible value. In this experiment, the values are only 0 or 1, but expectation is somewhere in the middle, right. It's p, which can be half, or it can be 1/3, or it can be 1 by 100 or whatever, right. It can be a biased coin. So that's the first major example. Second is its sum, and it is called binomial random variable. So if we repeat the prior experiment, n times, then how many times head appears? Okay, this is what we are interested in. So this is the random variable x. Okay, that's the definition of x. Number of heads in n tosses. So here the mass function is probability that x is equal to I. So I heads out of n exactly, right. So that possibility is which of these tosses were heads. So that's n choose I many times, and each time the probability associated is p raised to I times 1 minus p raised to n minus I, right. So that's the mass function, and based on this you get the expectation. So expectation is sum of probability x being I times I. It can be either 0 head dot n heads, and which further expands to n choose I times p raised to I times 1 minus p raised to n minus I times I, which you can simplify quite easily actually. So you just, what you do is this n choose I times I you write as, bring out n p and get n minus 1, choose I minus 1, p raised to I minus 1, n minus I. Okay. And this then you see is binomial expansion. Probably that's why we call it also binomial random variable, which is np times p plus 1 minus p to the n minus 1, which is np. Right. So, after this long calculation, what you get is n times p as the expectation. Now, is that a coincidence? Actually, we can give a simpler proof, okay, which will explain why you should get n times p. So, alternate way of looking at this is x is sum of Bernoulli trials Okay, you can write this as a sum of Bernoulli trials or Bernoulli random variables, because well, each toss is just a Bernoulli random variable, and using that you can calculate expectation of x to be summation expectation of xi, expectation of xi you know is p, so you get sigma p, which is just n times p. Okay, so this is a more natural way to understand this expectation expression, just n times the Bernoulli expectation. Okay, third is geometric random variable. So, this is toss a coin which is biased, probably with probability of head being p, till you get heads. Okay, you keep tossing it till you get a head. Now, what is the number of tosses? So, what is x1? I will call it number of tosses. To get a head. Okay, that is the random variable of interest. So, what is the mass function? Probability that x1 is k. So, the first k minus 1 are each of that outcome, each of those outcomes was tail, and the final one, kth one, was head. So, you get 1 minus p to the k minus 1 times p, right, that is the probability mass function. And what is the expectation? Expectation of x1 is, by definition, it is probability that x comes out to be k times k for all k. That is just the definition, right, and you get then and k goes from 1 to infinity, p is general. So, you do not immediately see what this value is, right, how does it depend on p, this is not immediately clear. So, let us do this analysis in a different way again. So, let us simplify. Let us rewrite this sum probability x equal to k times k as follows. x1 greater than k. Okay, let me correct this. This was x1 and not x. Right. So why can I say that? I can say this because in the first x sum, infinite sum, some value, say k equal to 10, that probability is being multiplied by 10, right? So you just want to make sure that this probability x1 equal to 10 in the second sum appears 10 times. So does that happen? In the second sum, x1 equal to 10 probability will be appearing from values 0 to 9, right? K equal to 0, it contributes, k equal to 1 it contributes, and k equal to 9 it contributes. So in the second sum it appears exactly 10 times. At k equal to 10 it stops the contribution, its contribution, right? So you can actually rewrite that sum as this. And I did this because computing this probability becomes easier. It's a simpler expression. So probability that x1 is greater than k basically means that first k were tails, right? So that is 1 minus p raised to k. And what is this? This is a simple geometric sum up to infinity. That's why the name geometric random variable. And you can see that its value is inverse of 1 minus p, which is p, 1 over p. Right. So this is a simple calculation that gives you 1 over p. And now thinking about this expression, it is somewhat natural because the probability of getting a head is p, which is a fraction, right? So the expected number of times that you have to flip to get a head should be around 1 over p, also in practice. Right? If you do this experiment, then you don't expect a head before 1 over p. So for example, if p was half, then you expect a head to appear when you toss a coin twice. Right? You are not very confident of a head in the first toss, but in the second toss you get more confident. In 2 tosses you are more confident. So that is what this expression is capturing, but you saw the mathematical calculation. Okay, and finally we have the negative binomial random variable. What is this? So toss a coin with probability of head being p till you get n heads. Okay, so you can compare this with binomial random variable definition. So there the experiment was for n times and you were looking at how many heads. Now you flip the scenario, you will keep tossing till you get n heads. So how many tosses? So what's this random variable xn? Okay, number of tosses to get n heads. So I'm calling it xn because this is just a generalization of x1, right? Probability mass function, okay, let me first write that. So probability that xn is k, that is in k tosses you get n heads, exactly n heads, that is k choose n places you can put the head. So head is probability is p raised to n, rest is 1 minus p raised to k minus n. That's the probability mass function, which gives you the expectation. So, k to get n heads you need to toss at least n times. So, you get sum over probability that xn is k times k, and that is just the following expression. Right. So, this is a more complicated expression than before. So, I do not know how to compute this. Let me now give an alternate calculation. So, you can write see, you want n heads, right. So, what is the expectation to get the first head? So, expectation for the first head is expectation of x1. Or let me do it like this. So, ith head given I minus 1th head. Okay, this is what I am looking at. So, first head, then after the first head, how far away is the second head, after how many tosses, then the second, after the second head, how many coin tosses required, the third head, and so on, right. You can actually break up the expectation in this sequence, and that is n times expectation of x1, which is n over p. Okay, so, believe it or not, this n over p is the same expression as the one in orange, okay, and this is also much better to appreciate, right. Why do you get n by p? Because, well, one head already requires 1 by p, so n head should require n by p. Now, let us look at a different family of random variables, which is continuous random variables. So, what does continuous mean? So, this we will define properly. Obviously, one thing is that you want to work with infinite sample space, that is for sure. When its range is infinite. And it is actually continuous. So, you can say that the range is all the real numbers, okay, and in these real numbers you are interested now what is the probability that x takes a value epsilon, epsilon being a real number. So, naively it seems to be impossible, right, because there are so many real numbers that and then the probability sum you want to be 1. So, actually x being some value, some real value, this seems to be 0 probability, right, in this big space. So, this does not help much, or this is kind of inconsistent with our axioms. So, we will actually need some new notions, and let us do that. And that is what we are calling continuous random variable x. So, what is that? It is defined by a function f from reals to reals to itself, called probability density function. Shortened to PDF, such that this probability density function will help you to define the mass, but obviously it will make more sense to talk about a range or interval where x is, instead of focusing on one element, right? One element probability will be 0, but what about looking at a bigger set like an interval of reals? And there this PDF will help. So, what you want is, first of all, okay, let me put one more thing here. There is fx, f sub x. Okay, let me clarify that. I'll put the big X also, and then for all AB, the probability that x is in the interval a comma b, that is given by an integral. Okay. So, now integration appears, which might seem shocking at this stage. We did not use integration till now. So, I will explain why this is happening, but let us just write down the properties first, which define a PDF, and then through that a random variable, continuous random variable. Second thing, then what you want is obviously if you integrate over the whole line, right, then you should get 1. Okay, so, if you integrate in intervals, then you get the probability of the random variable being in that interval, and if you expand it to the whole line, then you should get 1. So, this is what defines a continuous random variable. So, what is the meaning of this? So, one could interpret this f of x dot dx, can interpret this as a probability. Okay. Obviously, dx in integration is a formal variable, but you can also think of dx as just an infinitesimal value like epsilon, right. Your integration you can define as summing up in these small steps, in which then become infinitesimally small. So, in those terms, this f times dx, it should be interpreted as the probability of x being in the vicinity of x. Okay, so, this close to x means infinitesimally close. It is not that you can make sense of big X taking one value, but if you look at a small interval around this value small x, okay, and small in the sense of infinitesimal, that is very, very small. In the limiting case, it is just x, but formally it is vicinity of x. So, x, big X taking a value in that neighborhood or in that vicinity is given by f of small x times the vicinity size, neighborhood size. So, once you have this vague interpretation or this, let us say, physical interpretation, then you see that integration is just summing up these probabilities. and the sum is then the mass function for big X. Okay, and if you sum up over the whole line, then you get 1. So, in that sense this integration makes sense, is what you need, and with this the expectation is E of x equals the value small x, or kind of in the small vicinity, infinitesimal neighborhood of small x. What is the probability? That probability is given by f x x times dx, right. So, this you should think of as the probability, and first thing is the value. So, that is the expectation.